Uh, Today we're going to talk about mobile robot self-localization. I want to first show you this research platform um, at ENTC that we are using for projects and research on SLAM, self-localization and mapping, and autonomous driving and stuff like that. You can see over here uh, what sort of sensors are on board the robot. You can see up here the 3D LiDAR. This is a ranging device. It has laser, infrared laser beams going out of it, scanning right around. Okay. And if there are obstacles nearby, it gets the reflection. And if the reflection comes um, in a very short period of time, it knows that there is something at short range. Okay. And if you don't see any reflection, it knows it's fairly free space. So it has so many beams going out of it, and then it can figure out what's around it. In addition to that, it has RTK GPS rover unit over here on top of the LiDAR sensor. And that gives the position, okay, latitude, longitude position. Maybe you can regard it to XY position on the plane. But remember, we are not talking about perfectly flat surfaces. The robot is moving on, right? There are bumps and slopes, etc. So therefore, it's not just X and Y. The elevation also has some uh, significance here. In addition to that, you have wheel encoders. You can see over here the two motors driving the two wheels. And as the motor turns, we get the from the wheel encoders, right? How many turns the wheel has turned. In fact, not in terms of how many turns the wheel has turned, in terms of pulse count. So these encoders generate so many pulses per revolution, few thousand pulses per revolution. So that if you get one pulse or couple of pulses, it means a very small turn in the motor, maybe a degree or half a degree, something like that. Okay. And if you know how the two wheels turn, right, you can figure out how far the robot has gone and the curvature of motion and all that, right? If you have mathematical model. And using that, you can figure out where the position, where the robot is with respect to when you last estimated the position, how far it has gone. Okay. So self-localization has this kind of setup always. You have a mobile platform, and on top of that, there are a lot of sensors. Okay. And each one gives you some indication about the position or change of position with respect to a previous position. As the wheel turns, you can figure out where you are going, how much, how far, and all that, the direction, the turn, etc. And RTK GPS also positioning device. That is a global positioning device, right? And the LiDAR tells you what is around you. Now, if you know the area pretty well, and when the LiDAR says you, this is what I see, what is around me, right? Then we can figure out probably you are there in that location, okay? If there's a huge building and the robot sees something similar to a building, you know the robot is near that building, okay? Something like that. So in addition to that, you have the other sensor, IMU, inertial measurement unit. This is to figure out your posture, whether the robot is standing upward or slanted to one side or pitching down, up like that. It tells you about the terrain, okay? How flat or how um, awkward the position is of the robot, because all of these measurements, particularly the LiDAR, right, um, will provide you some different information if there is a tilt in the robot, right? Of course, RTK GPS is immune to that. It doesn't know the posture of the robot is, right? Wherever it is, where the sensor is, it gives you the GPS position. And also, if you look at the wheel encoders, sometimes when it is going through uh, a bump or a trough, then you will actually move a bit more than what you actually move on the road. Okay, so and if you don't know that you are actually going through a bump or something, right? You figure out, okay, you have gone too much on one direction. Okay, one of the wheels going over a bump, right? If you don't know that there was a bump, only way for you to know that is the IMU sensor. It tells you all of a sudden your posture changes. So you have to correct your wheel encoder saying that, oh, this part is actually not a flat motion, it's going up and down, right? So therefore, you should not take that as a linear motion on the surface. So this will give you some sort of indication, okay, how you can combine these different types of sensors in order to estimate your position, okay, as accurately as possible. And mind you, none of these sensors are perfect, right? If you have, is perfect. If you have one single sensor which gives you your position, you don't need anything else, right? Unfortunately, it's not the case. If you look at RTK GPS, you might think it is the most accurate. Yes, it is, but it's not fast enough sometimes. And also sometimes there are outages, right? You don't get RTK GPS at all times, right? When there is an outage, you need to have other redundant sensor systems to keep you going. All right, so let me show you this little video of how it is um, it is in action, right? So outdoor self navigation. You can see the robot coming from right hand side of the ENTC building. It's navigating itself. It has given the destination to go, okay, and it is following a path to the destination. So destination is in front of the building. And you can see people are talking, saying that there is a vehicle coming. Whether we want to stop motion, no, it's not. Robot knows what is around it and it knows how to steer away from the obstacles. Now it is going a bit closer to that vehicle because it wanted to avoid collision with the other vehicle, which was in motion. And now after avoiding the collision, now it tries to get away from uh, the vehicles. You can see it's right in the middle of the road, trying to keep same distance on left and right hand sides. Okay, right. So now you know about the sensor systems and how the robot can use these sensors to navigate itself. First, to figure out where it is, right, in the map, and then plan a trajectory path from where it is now to where it wants to be at the end, the goal point, and then plan the trajectory as uh, safe as possible, keeping same distance, right, from the obstacles around it. Now, this is a LiDAR map. You can see the buildings familiar to you, Sumanadas building and ENTC building, right? You can see green colored dots, yellow colored dots, and red dots. You can see that. These red dots are the positions of the robot. At each position, it scans around, right, 360 degrees and mark on the map what it sees. So if it and it knows the distance also because these are laser. beams, right? Laser ranges. So depending on the time to reflect, right, it knows how to calculate the distance. So the yellow areas are the free space. Okay. Green and black, other areas are actually not very safe to navigate, right? So this is the first thing robot needs to plan its trajectory. Okay, there should be continuous connected path, completely yellow, right, from the present position to the goal position. And here you can see as the robot moves, maybe probably near the ENTC building, somewhere over here, right, like that, it goes in this triangular road, and while it is moving, right, and then it is coming back to the same point over here, right, it combines all of these things, right, it has RTK GPS, it knows the position, right, and then the laser reflections, right, around it, so that you can actually mark on the map the green areas, right? So this is traversability. We call it traversability map. If you see these green areas, that is traversable, and black areas not traversable. All right. Now think for yourself um, how easy or how difficult or how accurate it is to build such a map. If you have very accurate GPS positioning, of course, you can connect these dots, okay? You can connect these dots because you know your position is right. What you don't know is what is around you, okay? Then you can map it. But if the GPS positioning is not very accurate, you are actually trying to incorporate what your observation, what is around you, right, at a different location, not the right position, not the correct position. So therefore your map will be bit awkward, maybe too squeezed, compressed, or elongated in one direction than the other direction, so it will not be to the same scale and all, right? So these are the problems that you have to deal with when you try to get a copy of your environment, right? Copy of your environment. This is a copy of your environment. Now, if if there are errors in these maps, of course there are. You will find in a tough situations when the robot is actually navigating on the ground. Okay, on the ground, because the map it has already created, maybe this one, and when it is moving, what it sees around are slightly different, not the same. Okay, so therefore the robot finds itself in a situation where what is said to the robot as the map and what it sees right from through its sensors are different, slightly different. So in that case, there should be special algorithms to handle these scenarios or some computational methods to like evolve the map based on the observation. Okay, this map that you originally build, right, and give to the robot as reference map to plan everything, right, is unfortunately not very correct. There are errors in different areas. So it has to evolve as the robot moves. Okay. So in a way, this is very much what we do as humans, right? When we walk around, we look at what is around us. If you are going into an unknown area, this is the first thing we do. Okay, we are very vigilant what is around. But if you move into an area where you go in and out daily basis, sometimes you don't worry what is around. Even you can walk with blind eyes, okay, like autonomously, because it's so familiar to you. And you know that it is very accurate in your mind. You don't have to actually get the information and update yourself. Okay. Now let me show you this one. This is what's happening inside the robot. Now you see top left point cloud. Actually, point cloud is this one. We call it a point cloud because it's points, millions of points, right? And we call it point cloud. So when you have the point cloud, as a robot moves forward, right, maybe you can have this point cloud updated in about 10 hertz or so, right? Um, and you do the segmentation kind of thing and then figure out the features. Okay, features. So features are very, very important. What are features? Maybe static features like trees, buildings, and vehicles sometimes are considered as features, because when you first take the robot along that road, whatever stopped vehicles that were there are considered as obstacles, because the lidar doesn't know whether it is a car or piece of rock or building, whatever. It doesn't know that. It just get the reflection and figure out, okay, it's not traversable. That area is occupied by something. So all of these things are features. But next time when you come to that point later on, right, the vehicle is not there probably. In that case, it doesn't understand what it is, right? But there's no harm. But if there is another new vehicle coming, right, as the robot moves, and that was not there when the map was built, right, then robot is in great trouble. How to deal with it? So immediately robot has to take the scans and identify that there is a new object here, and robot doesn't know whether it's a new object or it's static object, but robot uh, maybe robot is in a different position, not actually the position thinks it is now, right? So therefore all sorts of uncertainties come into the picture. If the robot is pretty sure I'm in this XY position and there's a new object that was not there earlier, right? It can figure out, okay, how to avoid this one. It doesn't know whether it's a car or a human or something else, but it tries to avoid collision, right? Try to keep away from that obstacle, right? So this is the life of a self-navigating robot, okay? Because it doesn't understand what it is, but it only knows there's something there and it has to avoid going into that object. So once you have the features, and we go to LiDAR odometry, right? Based on LiDAR, you can plan your trajectory, safe trajectory from one point to another. All right. So this is the high level thing. I think uh, you understood the big picture now. If there's any questions, you can ask now before we get into
So
details. Yeah.
what is this 10 hertz means? That means 10 points per second.
No, no. It is like 10 times a second, every 100 milliseconds, right? It takes the point cloud. It is moving slowly. Robot is moving slowly. It's not at the same time, right? So every 10, 100 milliseconds, it takes a scan, takes a scan, takes a scan, and gradually build the map. You can see it over here. Say these dots, right? This is not 10 millisecond dots, of course, right? But assume this is, sorry, 100 millisecond dots. Assume it is. So in one dot to the next dot, right? It's about 100 milliseconds, and it takes the scans, right? And then combine together all of these things. If you look at one scan, it's not like this one red dot and what is around it. That is one scan. Okay. Any other questions, please? All right. Then I I want to open the lecture note here. You can see it now. So let's talk about how this is done. Right. So you have seen the robot, you have seen it's moving. So therefore, these diagrams you can understand pretty quickly. Now, what you see here is the robot, right? Maybe the say two front wheels. Okay, two front wheels. And then it moves forward and it turns to left, right? And this is the next position. All right. There's a slight uh, motion, all right? Two positions of the robot in motion. So the L here is the length of the left side wheel. Okay, how far the left wheel has moved, and the R is how far the right wheel has moved. So if it is turning to the left, the right wheel moves little more than the left wheel. Okay, so the two distances are L and R. And also P is the position of the robot. You can safely say, according to the diagram, it is the midpoint of the two front wheels. Okay, and the distance between the wheels is like W here. And if you look at the curvature, right, this curvature is actually defined by this center of rotation C and the radius R. So from center to the left wheel, the distance is R. So it is actually going through a little circular arc, right? It's not a complete circle, but momentarily it's a circular arc of radius R. And with respect to the robot, the center of rotation is at a certain point labeled as C. And the angle along this circular arc that the robot moves, right, is alpha. Okay. Right. Now, what about L and R? How do you know the distance the left wheel travel? Well, it is as simple as this. The distance traveled by a wheel, right, is actually the pulse number, how many pulses that you receive from that wheel encoder, left wheel or right wheel, times a constant. So when you purchase this motor with the encoder, it says, okay, so how many pulses per revolution, right? How many pulses per revolution? And once you put it on the robot, okay, and there's a wheel and there's a wheel diameter, and you can do the testing. Okay, so you turn one round of the wheel and calculate how many pulses that you receive from the encoder, and you know the distance, right? Distance on the ground is for one round of the wheel is 2 pi, and the radius 2 pi times the radius of the wheel, and that is distance, and the pulse count is already there in the data sheet, or you can measure it yourself, and you can find out this constant distance per pulse. Okay, so if you read the pulse counter now, you have a certain value, and read the pulse counter after about 10 milliseconds, right? Pulse counter has changed, and you know how much, right? By how much. You can put it over there to this equation and calculate your left and right wheel distances, the distances the two wheels travel on the ground. Now, with the knowledge of R and L, so this is happening every, say, 10 milliseconds or 100 milliseconds, right? This is a repeating thing. Every 10 milliseconds, 100 milliseconds, you have to do that. And also you can write these equations. R, right? The length R is this capital R times alpha in radians, right? You know that. Radius times the angle in radians is the distance traveled. So L is equal to alpha times R. Similar way, you can write down this equation for R. The right wheel is alpha times R plus W, because this time for the right wheel, the radius is actually R plus W. So you can write these two equations, number one and number two. Now, once you deduct um, uh, one from two or two from one, either way, doesn't matter. So let's say R minus L, right? R minus L, 1 minus 2 is equal to alpha times W, right? Alpha W, and there you can find out alpha. Alpha is R minus L over W. So R you can calculate recursively, right? Every 10 milliseconds, 1 milliseconds. L can be calculated the same way. W is a constant, so you know alpha. It's a very, very small angle, and every 10, 100 milliseconds, you calculate your alpha. So once you know alpha, you can put it into equation number 4. L divided by alpha is equal to R. There you are. You know the radius of curvature, right? Again, it's not a constant. Every 100 milliseconds, it changes, right? As the robot moves. Sometimes it moves left, sometimes it moves right. Okay. Sometimes it's a very tight corner, turns quite a bit. Sometimes it goes to almost like a tangent, right? Very shallow curvature. Right. So now we are comfortable with these equations 1, 2, 3, 4. And what if alpha is 0? Well, you will know it if the moment you calculate R and L. When R and L are equal, right, the robot goes straight. It doesn't curve, right, to the left or to the right. So in that case, R and L are equal to each other. So therefore, we don't want to calculate alpha. And we don't want to calculate R either, because it will be, if you try some constant divided by 0, it goes to infinity. Okay. So equation 3 and 4 are also all right. Now, let's look at this diagram. So it's about center and the position, C and P. Now, this is a bit cluttered, but I'll explain every bit of it so that there's nothing that is more challenging for you, I hope. Now, you can see it over here, a world coordinate frame, right? Everything is measured with respect to a world coordinate frame. So let's say it is this one, X and Y axis, right? And this is the robot's position, all right? Robot's position, this one. So, now, you can see the robot's coordinate frame, right, is disoriented, okay, with respect to the world coordinate frame. It is actually tilted more towards right, okay, a clockwise motion. And this is the forward axis, this is the lateral axis. You can say this is X, this is Y of the robot, right? And this orientation is represented here by theta, right? The robot has turned by an angle of theta, okay? Now, if you look at the x-axis over here of the robot, right, because of this theta disorientation, you can write down the unit vector of the x-axis of the robot as sine theta minus cos theta, x coordinate and y coordinate, all right? Whereas the forward direction of the robot, or y-axis of the robot, the unit vector is cos theta sine theta. Pretty obvious, right? When the robot is oriented theta degrees, right, clockwise, its y-axis and x-axis unit vectors are written like this: cos theta sine theta for y-axis, sine theta minus cos theta for x-axis. All right, good. Then at this point, this is the initial point of the robot, and now it moves. What we did discuss earlier, it moves a little bit, maybe 100 milliseconds, and now it's here, new position, P dash. So P goes to P dash. Here it is a leftward curvature, right? Very small angle, alpha. And the radius of curvature is R. and this is the new position P dash. So now the orientation of the robot changes from theta to theta plus alpha. So it goes this way. The angle is measured anti-clockwise. Initially it was theta clockwise, but now it moves anti-clockwise by alpha. So the new orientation is theta plus alpha. Okay, the total angle. If you have any questions, please ask me. Spot on, okay, before get going. Do not accumulate your questions towards the end, right? Get it solved then and there. So here P is the position of the vehicle, the robot. C is the center of instantaneous rotation. So remember, this is instantaneous rotation. This changes next moment. Next 100 milliseconds, you get a different C, different R, different alpha. Okay, numerically. Now, uh, what is the equation you can write over here for C? Well, if you look at this triangle, it's just vector sum, right? The position vector of point C is the position vector of point P, right? Minus this vector from P to C, isn't it? Right? So you can write C position vector at this point is equal to P position vector here minus what is this vector? Well, the total length is R plus W over 2, right? Because it's the radius. We have calculated earlier the radius plus half of the distance between wheels, that is W over 2. Now you have to put the direction. What is the unit vector along that direction, right? So because you have put negative already, so therefore you can take this direction, which is sine theta minus cos theta. Put it there. And it converts the length into a vector. Equation number 5. So if you know P, we assume that we know previous position. The problem is how to calculate the next position given the previous position. All right. So P is known, R is already calculated, W is a constant. Sine theta cos theta is known because you know theta. The previous position means orientation heading also, right? Theta is known. So you can use equation number 5 to calculate C, right? The point of instantaneous rotation or center of instantaneous rotation. Why we want to calculate C? Because using C, we want to calculate P dash, new position. That's why. How do you do that? You do it in equation number 6. What is that? P dash, this vector over here, is equal to C. Now we know it, plus, now you can see this is R plus W over 2 again, this distance, okay, this distance, times the unit vector in the same direction, right, x direction. Now it is changing from sine theta to sine theta plus alpha and minus cos theta to minus cos theta plus alpha. All right, the same equation. This time in equation number 5, you use available information to calculate the instantaneous center of rotation, and then in equation number 6 you use it to calculate P dash, the new position. All right. Now with that, you can do a little simulation. I'm going to give you this as an assignment, right? You will, I'm sure you will enjoy this, right? How you can use the wheel encoders, right? No LiDAR, no RTKGP, nothing, just the two wheel encoders. And you keep watching the wheel encoder values, right? And then you do the odometry. Odometry means you calculate your future position just by looking at the wheels. So we call it wheel odometry. Okay, if you use something else, you use that thing, odometry. But here it is wheel odometry. Now, You have altogether 6 equations in wheel odometry algorithm, right? And the simulation code has only few steps, not too many. How do you start the algorithm going? Oh, well, you need to give P, the initial position, right? That is X and Y with respect to a world coordinate frame, and theta, your heading, right? And also you have to give what is the distance between the two wheels, right? That is W. So these are the initial information you have to provide to the algorithm. Then you start the motion and read every 10 or 100 milliseconds the two wheel encoders. How many pulses are there between then and now, last time and present? Okay. So you convert that into RNL, left length, right length, and you calculate alpha using this equation, R using this equation. And then what is this one? This is the position, instantaneous center of rotation, C. So C is a point on a plane, XY plane. So it has two coordinates, X and Y. CX and CY are the coordinates of that point C. So it is equal to X and Y. This is equation number 5, actually, this one, right? Equation number 5. So you apply it over here to calculate Cx and Cy. And also, because you know alpha, you can update your theta. What is the present heading? It is theta plus alpha. All right. Then you use equation number 6 over here to calculate your new position. That is P dash. It has two coordinates, X dash, Y dash, is equal to this is equation number 6, C plus this equation. And you calculate your present position. Okay, P dash. However, when you get R and L are equal, you are in this situation. So that theta dash is equal to theta. Your heading is not going to change. You are moving along that direction. In that case, new position X dash and Y dash are calculated this way. X plus L cos theta, Y plus L sin theta. Okay. So without any curvature. You don't need to use equation 5 and 6 because you are not going through a curvature. Okay, straight ahead. This is a very simple algorithm. We call it dead reckoning. Dead reckoning. One of the problems in the dead reckoning is that every time you have to calculate your two wheels, left and right, and you assume the wheel pulse count is proportional to the horizontal distance on the ground, on the plane, horizontal plane of the ground, which is not a very accurate assumption because the robot goes over bumps and troughs and all that. Therefore, actual count is not the actual distance on the ground. So therefore, there are errors always. And if you don't know what the error is, what the correct part of the reading is, and these errors are getting accumulated within the algorithm. So therefore, your update of your position, which is P dash, and the next moment there's another P dash, X 100 milliseconds, another P dash. What will happen is that all these errors that you made in the process gets accumulated. There's no way for you to get rid of that. So if you continue for some time, you will see your estimated position is far from the actual position. Actual position is what you see on the ground when the robot is moving, right? You know where it is actually, right? But robot thinks that it is in a different position. Okay. Now this is without any other observation, without LiDAR, without GPS or anything. All right. Entirely using the two-wheel encoders. So I'm going to give you a little assignment on this. I will write it down and post on the course website. You can download and work it out. And in that assignment, I think I'll give you, I'll ask you to plan a trajectory, right? Plan a trajectory, maybe a straight line from point A to point B or a curvature, whatever it is. and that is your reference. That is your reference. And then I'll ask you, okay, run this algorithm and look at the wheel encoders, and time to time you can generate your wheel encoders, right? And then put it into this algorithm and calculate your position. That is the estimated position. Okay, estimated position. Then you can plot the two graphs, actual path and estimated path. Okay, robot is moving on the same line. Let's assume that this algorithm is running, but this algorithm is not used for any controls, right? In this stage, let's assume this algorithm is not going to generate any control commands to the mobile robot, right? Robot is moving along that path, and from that path you generate the wheel encoder values and put it into this algorithm and ask the algorithm to predict the position to see how close the prediction is, right? And at the same time, to make it more realistic, I'm going to ask you, okay, why don't you add a little noise to the wheel encoders? Because every wheel encoder has a little error. So I'm going to ask you, okay, generate some random errors and add that to the wheel encoder values, right? Okay. So then with that noise addition, you predict the position and see for yourself what the robot thinks its position is. So this will be really interesting exercise for you so that you can understand uh, the real nature of wheel encoder based localization, and the name given to it is dead reckoning or wheel encoder based localization. Any questions up to now in terms of the equations that I presented, already 6 equations, or in terms of the concepts, localization concept? Any question?
In coordinate frame assignment on the robot,
Yeah.
it's made along the x-axis and perpendicular to it y-axis, like uh,
Yeah, this one over here.
wheel axle x-axis and center point and perpendicular to it take as y-axis.
Yeah, according to this diagram, yes. But you can change it the way you want. If you prefer to have X along the heading and Y lateral to that, that's also fine. That's also fine, right? So I have done it here because the world coordinate frame, wanted to get the world coordinate frame Y vertical, X horizontal, because everybody is more comfortable working with that kind of world coordinate frame, and accordingly, I use the smallest angle as the heading theta, so that my Y naturally becomes the heading direction of the robot. Only for that reason I use that. You could use any other frame assignment, right? As you said, heading X direction, wheel axis Y, fine. Accordingly, figure out what the theta is. Okay, so theta means Y to Y or X to X. Okay, between two frames. It's not from X to Y or Y to X. So therefore, your theta, if you change Y and X, would be what? Minus 90 minus theta or something like that. Okay, but the rest remains the same. Any other questions, please? All right. So let me move on. Here, I want to start somewhere in the middle of the document here. Dead reckoning path errors. We have already discussed that you just cannot predict your position looking only on the wheel encoders. Okay. And if you continue this for some time, your estimate will be more and more inaccurate, okay, from the actual position. And here you can see some graphics on that. So I start my mobile robot over here, start point, and move this way, right? And robot is actually moving in this red line. You can see the red one, maybe it's not very red, right? So this is the actual path of the robot, this one. The curved path inside, right? The smaller ones. So this is the actual path of the robot, actual path, right? But this is your assignment basically. Now, the robot estimates using the 6 equations, the dead reckoning algorithm, and it calculates its position as this one in black color, right? This is what the robot thinks its position is. Now, after a while, you can see the two endpoints, the red one here and the black one over here. They are drastically different, right? So the more you drive, the more you continue along with the dead reckoning, higher will be the errors. So you only accumulate errors, right? Errors on top of previous errors, and you are getting increasingly away from your actual position. So luckily, you are not using your localization result to control the robot. If you do that, you will be in a disaster. Okay, this is independent driving. You're driving the robot. You know where the robot is moving. It is safe. It's totally under control. But on a parallel algorithm, you run the dead reckoning and to test whether how accurate the dead reckoning is. Right? You're not using dead reckoning to control the robot. Remember that. Okay. Now, if you want, now you can think about various things. We can improve dead reckoning. Of course, yes. Because if you look at the algorithm over here, you can see there are 6 equations and figure out what you can do about this, right? To reduce these errors. Well, if you follow through all these equations, you can find out there's something that you can play around. That is W, the distance between the two wheels. You go and measure it again. Maybe I have got it wrong initially. You measure like um, 35 centimeters, but you measure it again, and now you see it is 37 centimeters. Okay, like that, you can try it out. The constants you can measure again and more accurately and put it into that algorithm. So then you can maybe improve it actually like this. Now here you can see the actual path of the robot is again in red and other one is black one. You get as close as possible, right? But fundamentally, there is these errors because of noise and all that, right? You cannot get rid of that no matter how hard you try. So therefore, on top of that, you have this accumulation characteristics. Is very, very dangerous, right? Error accumulation is a very, very dangerous process. Unfortunately, in dead reckoning, it is the case. So therefore, you are getting these errors. Okay. Therefore, uh, we need to bring in some other sensor system, right, to improve the accuracy or to work together with wheel encoders. So we are not going to dump this dead reckoning algorithm saying that this is not good. No, what we do is, all right, so we know it is partially successful, but it's not acceptable yet. We want to bring in additional sensors to work with the wheel encoders to make it better, right? So what we are going to do next is to bring in the LiDAR. I think in the video you saw that, the LiDAR. So when you put the LiDAR, maybe right over here, this is your robot's position P, right? If you can get the LiDAR right on top of that position, so much the better. But it's not a, compulsory requirement. You can put your LiDAR any point, right, on the robot, as long as you know the relationship between the robot's coordinate frame and the LiDAR sensor's coordinate frame. So remember, LiDAR has its own coordinate frame. Okay, it has its forward direction where it starts the beam, right? So it starts turning 360 degrees around that forward direction. It's like the zero longitude axis, Greenwich zero. All right. So from that point, it starts counting. So this is a very simple relationship between a LiDAR coordinate frame and the robot's coordinate frame, right? If you know the distance between the two centers, let's say D, right, and the position of the LiDAR with respect to the robot is given by this equation, right? P plus D cos theta sine theta. So this is the y-axis unit vector along y direction, and d is the distance. You add this vector to p. P is the vector of the robot, right? Robot's position with respect to the world coordinate frame, right? And to that you add this quantity, and it's the position of the LiDAR sensor with respect to the world coordinate frame. Okay. Now you have to keep this thing in mind that when we say positions, right? Sometimes we refer to the robot's coordinate frame. Sometimes we refer to the world coordinate frame. Okay. Now, when you are in a self-navigation problem, more often than not, you refer to the world coordinate frame. And your sensors are attached to the robot so that all of the measurements that you get through the sensors are with respect to either its own coordinate frame, sensor coordinate frame, or to the robot's coordinate frame. And you need to transform them with respect to the world coordinate frame to place them right on the map, global map, right? Coordinate transformation is something I've already done, right? I think there's no problem for you to understand that part. Okay, now here you can see how the LiDAR works. So I strongly recommend you go to the internet and figure out some videos on LiDAR and localization with LiDAR, SLAM, etc. Right after this lecture, you will be able to easily understand the contents on these videos and other material, right? So this is simply how the LiDAR works. So you can see the LiDAR sensor right in the middle and start somewhere over here, the first beam, second beam, third beam, fourth, like that, all together in this particular case, say 660 beams. So when you deal with, when you use a LiDAR, this is something you need to know. How many beams are there? This particular case, 660. Oh, of course, in the back, there's certain area that you don't see. Okay, right. And every beam, either it does not reflect, whether if there's no obstacle, it just go forward and it doesn't come back. But when there are obstacles like this one, and this one, three obstacles here, the particular beam gets reflected. So when that particular beam comes back, you know the direction of the obstacle with respect to the LiDAR sensor. Okay. And also looking at the reflection time, you know the distance, how far away that object is. So you know the angle and the distance, angle and the distance, angle and the distance. For all of these beams, and you can find out where the obstacles are, how many obstacles are there, whether they are big obstacles, small obstacles, and also whether they are close by or far away. All this information can be figured out. So this is the LiDAR data sheet. If you can see over here, this part, right? Uh, is just a data file. It has few columns, right? Or many columns. First one is time. Okay, at what time you are taking this reading. And after that, you have data one. This is the first beam over here, right? Then data two, second beam, data three, data 660. All these individual beams indexed by number 1, 2, 3 up to 660, and it gives you distance. After all these things calculated, you get this data file. Okay, right. Now, if you plot a graph of what you see from the LiDAR, it will look like this, right? And there you can see every time there is every angle where there is an obstacle, you get a shorter reading, shorter distance, right? So like over here, on the left, far left is 0, that is the first beam, and the far right is 660, that is the last beam, right? This is actually the angle, and I put it into a straight line, okay? So when it detects the first object over here, right, it suddenly gets the distance short distance, right? Suddenly the distance changes from this value to this value. And after a while, it increases again. Think about a tree, right? When you scan your laser beam, right, say index 20, goes through the left side of the tree trunk, so it doesn't come back. That is laser beam 20, right? And 21 hits on the tree, and it reflected back. And suddenly there is a drop in the distance. Okay, this is 20th beam, this is 21st one. And from that point onwards, 22, 23, 24, up to about 30, these beams all struck on the trunk of the tree. All right. And then 31st goes to the free space. There's no tree or anything there. It goes free and it doesn't come back. So this is like that. Okay. So it's very easy to interpret the LiDAR map like this. And you can see this is an obstacle, this is an obstacle, this is an obstacle, this is an obstacle, something like that. Okay. And also you can see this obstacle is a broader one, and this obstacle is a narrow one, maybe a bamboo tree or something. And this is probably a jack tree or something. Okay. Like that. You don't know actually what these things are, but you can see there's a broader object or a small object. And also you don't know whether it is a building, concrete building, or steel structure, or piece of a cardboard box on the ground, right? The material and soft or hard, robot doesn't know anything about that. It consider everything as obstacles, right? Uh, there are errors also in the LiDAR map. You can see somewhere over here. Suddenly there's a little spike kind of thing, negative spike. It goes to 0, and you cannot interpret what this is, and you can disregard this as an error. Okay, erroneous signals. Just disregard. So if you get very short readings, very close to the robot, and of course you know it was not detected earlier, and suddenly there's an obstacle here, very short distance, few centimeters away from the robot. Most likely it's a error signal, right? Don't worry about it. And also there can be a tree behind another tree, a big tree and a small tree, like this, for example, next to each other. So in between there's no space, so that the beams hit on the first tree and the following beams hit on the next tree as a continuous thing. So if you look at the LiDAR map, you will see something like this. There's a tree, right, close by, and then there's another tree a bit farther away, right, and partly covered by the first tree. So it will look like this, 2 steps down. So you can interpret that, okay, very easily. So this is kind of LiDAR data pre-processing. When you have sensors to measure certain things, one of the first things you need to know is that to refine the data, okay? Do not take any garbage data into the process, because if you get garbage in, garbage out, okay? Don't do that. Remove the garbage upfront and get only the genuine data to the process. So how do you remove these garbage data, like spikes and all that? It's by calculating the rate of change. One very simple way, rate of change. So how do you do that? So here you can see the beam index, 50th beam, 55, 59. It goes like that. Sorry, these are the ranges, 50 centimeter or whatever, 55 centimeter, 59 cent, like that, right? Uh, Increasing, and this zeroth beam is the first beam, second beam, like that, right? So what you do is you calculate the rate of change from first beam to the second beam, second to third beam, right? One way you can do that is that, okay, you deduct, say 59, deduct 50 from 59, that is beam number 2 minus beam number 1, sorry, beam number 0, divide by 2, to the two steps, two angle steps, and you get the derivative. So if the derivative is very high, you know it's an error. Okay, practically you can figure out what sort of derivatives are practically acceptable. And more than that, any derivative, right, bigger than that acceptable range, you consider as noise, erroneous data, just drop it. Okay, so you can do that. So in this pre-processing, this data is actually removed, right? And we continue this line without going deep down over here, right? And also this derivative thing, when you apply for the entire laser reading data set of maybe here is 660 data points, right? You can see every time you first detect an obstacle, right, you get a negative spike, right? And every time you clear the obstacle to the free space, you get a positive spike. So negative spike on the left, positive spike on the right, like that. So it's a clear signature of an obstacle. You can think about the tree trunk, okay? One side, negative spike, other side, positive spike. Small spike, not very big, okay? Small spikes, like that. And sometimes you can have two negative spikes and one positive spike, and it indicates, okay, there's a tree, and behind that there's another tree, something like that. Okay, so nothing to worry about. All right, now we know about LiDAR, how it works, how to pre-process LiDAR. Now it's time to see how we can incorporate LiDAR data to localize the robot. So every time, remember the video you saw, right? Robot was moving and you saw the LiDAR map, right? So this is the theory of how this is possible, right? So now if you figure out the ray index and the range, so this is the data combination. You have the ray index and the range. So if I pedal back, I can show it to you. This is the ray index. Sorry, the 0, 1, and so on. This is the ray index. And this is the range, right? Ray index 0, range 50. Ray index 1, range 55, like that. So when you have the ray index and range, you know it is with respect to the LiDAR coordinate frame. With respect to the LiDAR coordinate frame. Okay. Now, how do you convert this into the world coordinate frame, right? So you can do this using this equation very easily. You can see it over here. This is something we have done earlier, right? So what is it? You know the robot's position, okay? Because this is like recursive algorithm. You know the present position, you predict the future position. Future means in about 100 milliseconds, right? It's not far future. This is happening very fast, very quickly, in 100 milliseconds or so. So PR is the robot positions that you start off with, okay? And now you have moved, right? And laser scanner gives you uh, some information about what you see around. Let's say take just one obstacle. It says ray index 150, the distance is say 50 centimeters, something like that. Now it sees something with respect to its own coordinate frame, the LiDAR's coordinate frame. All right. So you convert that into robot's coordinate frame, right? That is R, X, Y means that one, robot's coordinate frame. Using this equation, you can do that. The little offset, where's that? This one. Okay. This one is what the difference between the robot coordinate frame and the LiDAR coordinate frame. Okay. So this is already there. You know how far away the LiDAR is with respect to the robot's position. So that's fine. So everything that you see on your LiDAR, you can easily, quickly transform to the robot coordinate frame, right? Now, after that, how do you convert it back to the world coordinate frame? It is by this equation, right? This PR is robot's position plus RXY is the obstacle position, this one. Obstacle is seen by the LiDAR, right, using the ray index and the range, and you convert it to the robot's coordinate frame, and then you convert it from robot's coordinate frame to the Earth coordinate frame, because you already know the difference between these coordinate frames, the robot and the Earth, and you know the transformation. Okay, how far away along X and Y axis the robot is, and what is the direction of the robot. That is known. So therefore, you know this transformation. All right. So which means what? This means when the robot takes a LiDAR scan around it, the moment it understands, okay, there are n number of obstacles around me, or you can say landmarks around me, and these are the positions of the landmarks, right? They're located at these angles with respect to my coordinate frame, and at these distances, right? Now you have this equation number 8 to calculate the positions with respect to the world coordinate frame, and then plot them on the world coordinate frame, world map. There are obstacles in these locations. Now it's not with respect to LiDAR or the robot, it's the world coordinate frame. Okay. Now let us do this. Now you have the robot, you are moving the robot under your control, right, along this curvature. As you move, right, the robot has these obstacles around it at some point, right? And it makes the LiDAR scan and figure out the positions of the obstacles around it, and then calculate using equation number 8 their positions, right? Now remember, robot knows its position only using the dead reckoning. Earlier you saw that, okay, dead reckoning. So therefore, its position is not correct. Now robot thinks it is going through the outer circle here, outer circle. This is what the robot thinks, okay? The robot thinks because it has only wheel encoders, okay? Using wheel encoders, the first 6 equations, it calculates its position, and then it has the LiDAR data now, right? And using LiDAR data, it converts the obstacles positions, right? Using equation number 8, all of these obstacles. And you can place these positions on the same map, global map. So what will happen? Here you can see the red dots are the actual obstacles. Say 4 trees in that area. You do this testing, okay? 4 trees, the red ones. You know the positions of these trees, but robot doesn't know. When the robot moves in, it gets the LiDAR map and calculate the position of the trees and transform them to the world coordinate frame and plot using these black dots. These black dots. Now you can see the black dots and red dots are not coincident. There is an error. The error is due to the dead reckoning error on the robot, because the robot doesn't know its exact position accurately. And there's a little error in its location estimation using dead reckoning. And this error is increasing as it moves, right? So therefore, whatever it sees around it, right, the obstacles, when the robot transfer that using its own position estimate, you get incorrect positions for the obstacles as well, right? You can see it over here as well. Errors of obstacles position increasing um, as the robot's position estimate deviates from actual position. So this is initially, right? When you start the motion, right, you have a small error in your position. Your actual position and your estimate position is not very far from each other, okay, initially, because you have not gone so far. So therefore, the the errors in the positions of the obstacles, the landmarks, are also not that great. So you get very small errors. But as you move along the trajectory, somewhere over here, there's a significant error in your dead reckoning, the position estimate, and therefore the errors between actual obstacles and the estimated obstacles is also big now, significantly big, right? So this is what happens. Now, can somebody tell me how can we use this information, LiDAR information, to correct the position estimate that we normally do with only the wheel encoders? Any suggestions, please? Can anybody suggest a technique? No idea? All right. Now, these red dots are the actual or accurate positions of the obstacles or the landmarks. And the black dots are the estimated positions of these same obstacles, same landmarks, right? Now, the difference is because of the errors in the localization process, because the robot's position and heading are not very accurate. That's why these differences are there. Now you can use these errors to change the position or modify the position and modify the orientation or heading of the robot so that these black dots, right, come as close as possible to their corresponding red dots, okay, and preferably coincide, right, fall right on top of the red dot. So the position change or heading change that will make that happen, right, uh, is the localization process here, right? So we will correct the errors in the wheel encoder base localization using the errors between the actual positions and the estimated positions of the obstacles, right? So this is what is called the feature-based localization, right? Feature-based localization, because features are actually these obstacles, landmarks. We use the landmark information and their estimated positions and try to change the estimated position of the robot so that these landmarks, the estimated positions, fall right on top of the reference positions, actual positions. When that happens, you have the best estimate of the position of the robot. Position means position and the heading both together. All right. So all right. Now we know what we have to do here to improve the accuracy of localization. Okay, to find out our actual position of the robot, which means we want to try to bring the black uh, path over here. This is the estimated path as close as possible to the red path over here, the outer curvature here. When we do that, the black uh, landmarks, will gradually get closer to the red marks. Okay? So you need to have that understanding right now. So as I have written over here, if the position of obstacles are known, right, the red dots, we know these positions x, y with respect to the world coordinate frame. Then the path of the robot can be accurately estimated using the error between estimated and actual positions of the obstacles. Okay, all right. So now we are going to develop this technique we call feature-based localization. Now, the first thing is this: you have to think like the robot, right? You have to think like the robot. Now, at a certain point, right, you know you are not on the actual path, right? You are deviated slightly from the actual path. And you know you have some landmarks around you, right? Given specific positions, right? We know accurately. And also, you know, based on your LiDAR measurement, you have some, you have detected some landmarks around you. Now, which one of these landmarks that you see is corresponding to the actual landmark, right? That is not very clear. Say, for example, in this illustration over here, it's pretty obvious. You have a red mark and black mark, red mark, black mark. It's pretty clear that the number one black mark is actually the number two red mark. Okay. So all of these red landmarks, let's say they have indexes, right? 1, 2, 3, 4, like that. And when you measure your obstacles using LiDAR, you have their index also 1, 2, 3, 4, right? So which black index is corresponding to which red index, right? It's not pretty straightforward, but you can figure it out. Let's say the closest red mark to each black mark, right, is I think the corresponding pair. So this is like pairing the reference versus estimate, right? Reference versus estimate. You need to find out which black one is closest to which red one and pair them together. Now, in a realistic situation, anything is possible, right? Sometimes you don't get two marks, red and black, closer to each other, right? They're little far apart. In that case, it's not a very wise to make a pair. In that case, you don't make a pair. All right. So pairs are the reds and blacks, which are closely apart, right? You have a finite number of these pairs and take those pairs to consideration, right? Do not take, even though you have so many other blacks, right? Estimated landmarks and so many other red marks, okay? Actual landmarks. You only take the confident pairs into the process. All the other marks you just disregard because we don't know to associate which one to which one. And if you erroneously associate um, an estimated mark, right, landmark, to not its corresponding reference mark, the entire localization modification is going to be affected. All right. So therefore, it's absolutely necessary that you get the accurate pairs, like what you see over here, right? So this is the first thing. So if there's no obstacle within this radius, neglect the estimated obstacle. So that is the rule. So each estimated obstacle, right? You identify an area around it, and if you don't see any reference marks there, you neglect that estimated landmark. Okay, and eventually you have some finite number of pairs. Finite number of pairs. What's next? Now we are going to do what is called similarity transform. So look at the name, similarity transform. So we need to improve similarity between the estimated marks and the reference marks. Okay, we want to actually bring them together and then put them on top of each other, right? So the transformation or the modification required is what is called the similarity transform. So we write it like this: R equals S of Li. So what is L? L is the estimates, all of these estimates, right? Measured landmarks. And R is the reference set. So you get the R's and L's from here, right? From here. So this is the L, this is the R. This is the L, this is the R, the pairs, okay? And then for all of these, for each of these measured mark, you do this transformation. What is that? So this is the Li, right? The measured landmark, its position, X and Y. It's X and Y, okay? You multiply it with the rotation matrix. So you rotate it some way and you multiply with a scaling factor. You scale it up and then you add it to a constant distance, some translation. So you can see the rotation, translation, and scaling, right? So these are the basic modifications you can do to a vector, to this measurement, to bring it closer to its reference. By this way, you can bring any point that you measure into any other point, the reference, okay, by selecting R, lambda, and T. Now the problem is very clear. How to find out the scaling factor, lambda, and the rotation alpha. Here also there's an alpha. This is different from the previous alpha, of course, right? And then T, the translation. Now here you can see in this diagram, the reference landmarks in red color and the measured landmarks in black color over here. So when you do this transformation, similarity transformation, what happens is that the red one and black one, they fall on top of each other, right? So this is the technique. Now, as I have written over here, right, lambda and alpha and T is Tx and Ty, right? Horizontal and vertical translation. So there are 4 parameters required for rotation, translation, and scaling of L to get it coincide with R. Very clear. Now let's say you have 4 pairs, right? So this pair, this pair, this pair, and this pair. You need to have 4 pairs to coincide each other. And if you want to do each and every pair, you get individual lambdas, R's, and T's, right? So that is not what we want, right? We have, let's say, 4 sets here. We want, let's say, you try to perfectly match the first pair, but Other three pairs are not matching. Then you try second pair, you want to have perfect match, and other three pairs, they don't match. So this is not what we want. We want to find out what is the best similarity transformation so that overall error is minimized, right? It's okay not to have even a single pair properly coincident, perfectly coincident. But if we get all of these pairs as close as possible to their corresponding points, so that the overall error, the total error is minimized. This is exactly what we want. Now, this leads us to minimization problem, right? Or optimization problem. Okay. And we have four parameters in the optimization problem: alpha, lambda, tx, and ty. So those of you who are aware of optimization, right? You can have these four parameters, all of these random values given to these four parameters, each and every one. You get a huge number of combinations, and you can try out individual combinations here for all four pairs, find out which lambda, alpha, tx, ty gives you the minimum error overall. So that is the optimization process. But it takes a long time to process if you want to walk down that path. Okay. So therefore, we need to be more smarter here, develop an algorithm which is efficient and faster. Okay. So what about least square estimate? Let us find out least square estimate, right? Of course, if you do the least square estimate, it's also harder, right? It is the direct solution of similarity transform, right? Uh, all of these individual errors, you want to get the squares and add them together, right? Like this over here. Can you see that? A lambda r li plus t. This is the similarity transform, right? The new position of the estimated value. So estimated landmark, its positions are now changed to make it more closer to the reference, and then you deduct the reference landmark from that one. So this is the error. After the transformation, this is the error. You get the square of that. So all of the individual pairs, right, in the set, you have to do this and add them together. So this is summation, right? And then you have to minimize it with respect to lambda, r, and t. T means tx and ty, right? This is your optimization process using least squares. And the direct solution using least square estimate, right? This format, least square estimate in this format is very complex. It's very complex. But least square is all right. So what we exactly want is least square based minimization of the error. But if you follow this path, it will be very computationally intensive and takes time. In real time, you won't be able to implement. So you saw the robot, right? It's moving in real time. This is a real time process, and the computer on board the robot has to execute these algorithms, right? So instead, we try to use um, the variable reduction technique here. So we reduce coordinates using these equations, and you can see it on the graphics here also, right? Look at that. What are we doing here? So there you can see L0, L1, L2. These are the actual measurements, right? Landmarks, their positions, right? And if you have so many of these things, you can add all these things together, right? Add all the x coordinates of all the landmarks, divide by the number of landmarks, and add all the y coordinates of the landmarks, divide by the number of landmarks. You get the centroid. So right in the middle is the centroid. That is L bar. Centroid of all of the landmarks, right? So the equation is very simple, like this, right? For the landmarks, equation number 13 over here, and also the centroid of the reference landmarks, okay? This time you add all of these RIs. RIs means Rx and Ry, right? X coordinates, Y coordinates. Add them separately and divide by M, right? That is your centroid of the reference landmarks, right? Then you define a new landmark like L dash by deducting the centroid from each landmark, Li. So there you can see Li is the landmark, measured estimated landmark, minus L bar, the centroid. So when you do that, you can see visually what is it. So when you do this for this a zeroth landmark here, this is L0 minus L bar, this one, right? Now all of these L dash, right, the modified landmarks are actually coming from the centroid. These red vectors here, this one, this one, this one, and so on, right? Coming from the centroid of the landmarks, okay? And similarly, for the reference landmarks, you can write it like that. You define a new reference landmark for each reference landmark, Ri dash, which is equal to Ri minus R bar. So you deduct the centroid of the references or reference landmarks from individual reference landmarks, okay? So this will reduce the coordinates, okay? Now we are not referring to the world coordinate frame. Now all of these vectors are actually coming from their centroids, okay? But remember, these two centroids are not equal, okay? Centroid of the R and centroid of the L measurements are different. Now, the other identity over here is that if you add all of the modified estimated landmarks, right, after coordinate reduction, the answer is 0. Okay. Now look at this one. If you add all these things together, right, the answer is 0 because L bar is defined like this, right? So if you sum up all these modified landmarks, you are actually adding all of the landmarks minus all of the landmarks. So it's 0. Okay. So remember equation, these two equations, right? When you add all of the modified landmarks, all of the reference landmarks, modified reference landmarks, right? The answer is 0. So with the modified measured landmarks, modified reference landmarks, you can write down the similarity transform this way, right? So our original transformation is at the first line over here, lambda r li minus ri plus t. So this is the similarity transform we want to implement. Then second line, we replace landmarks, that is li, with the new reduced coordinate format. So li is equal to li dash plus l bar. All right. And similarly for ri is equal to ri bar plus, ri dash plus r bar. So the modified preference plus the centroid of the references. Okay. T doesn't change. So you just substitute for Li and Ri. So the next line, what you do is you bring this Ri dash to the front and Li dash together with Li dash, right? And then middle part over here, lambda R L bar, this one, the first L bar term in the first term to the middle term, right? Plus T. Why we do that? Because this part is a constant. This part is a constant, isn't it? Lambda is a constant eventually, right? Because we are not actually trying to match every measured landmark to get it coincide with the reference one, right? Not individual ones, but we want to minimize the overall error, okay? So lambda is going to be a constant at the end of the day. R is a constant. L bar and R bar are the centroids. So once you know all of the landmarks, the centroid is a constant. Add them together. That's it. Divide by number of landmarks. And the T is also constant. Eventually, you want to move the entire set of estimated landmarks in x direction and y direction by a constant amount. So it's a constant. So the varying part is only here because Li and Ri are the modified landmarks and modified reference landmarks. Okay, right. So individual landmarks, they are going to be different. So therefore, this I index is there, subscript I is there. So with this one, we will introduce new variable T bar or T dash actually to replace this second term over here. Let's try to do the minimization. Now, S is the similarity transform for individual pairs, and S star is the overall similarity transform. Okay, so I would rather write down this as Si because it's individual to every pair, right? But S star is not that. It's a unique one. The minimum error or the similarity transform that is corresponding to minimum overall error. So a star can be written as a minimization process over here over I, all of these pairs, right? Can you see it over here? Lambda R Li dash minus Ri dash plus T dash. Get the Euclidean norm, right? The length of that error, right? And square of that. So add all of these together. So remember, once you have these errors, right? In fact, this transformation, right? This transformation brings individual measured landmarks. Okay, the other way around. This transformation, right, is responsible to move the references and the landmarks as close as possible, right? And therefore, when you do that in individual pairs, right, once you add them together, right, you get the overall error, okay? And sometimes these errors are positive and sometimes negative. So they can cancel out each other. That is not what we want, right? If it is negative or positive, it doesn't matter. It's an error. So we want to look at the square of the error. So that's why we write it this way in the minimization process, okay? Right. So then you can expand this, the Euclidean norm square into individual terms in the middle. So you get the first one, lambda R Li dash minus Ri dash, the first two terms, square, plus 2 times T transform, lambda R Li dash minus Ri dash. So you get the product between the two. This transform comes because these are vectors, So when you multiply, you need to look at individual vectors are actually column vectors, but when you multiply two vectors together, make sure one becomes row, the other one is the vector. So the transform is required, okay? And then the TI Euclidean norm square, right? So we have just expanded the overall error, right? Square sum of the error. We want to minimize the square sum of the error. So if you look at the first term, you keep it as it is, right? Second term, 2t dash transpose times summation of this one. Now we are bringing the summation to individual terms. We have three terms, three summations. So first summation, second summation, third summation. Okay. And if you look at the second summation, right, the second term over here, right, you can break this summation into another two, right? First one, lambda r li dash, and then the ri dash, right? So it will read like this. Lambda is a constant eventually, r is a constant. So it is summation of li dash minus summation of ri dash. Now remember, we have shown earlier that if you sum up all of these reduced coordinate landmarks, modified landmarks, and all of these modified references, right? When you add them together, the answer is 0. Okay, I can pedal back and show it to you like that over here and over here. Okay, so therefore, the second term over here is simply 0, right? From equation 11. So is that 11? Yeah, equation 12, yeah, 11. And this is 12. So 11 and 12. All right. So therefore, we don't have anything coming from the middle term. If you look at the third term, the summation of t dash square, t dash is a constant, right? So summation is constant times the number of pairs here, right? So if you get the obstacles and landmark pairs as capital M, it is M times t dash square. So now we have obtained this equation 15. So what is that? We need to minimize this summation over I lambda r li dash minus ri dash all things square plus m times ti square. Okay. So because these are squares, they are greater than or equal to 0. Then what is the minimum value? Oh, minimum value is 0. All right. If a function is always greater than or equal to 0 and you want to find out the minimum value, it's 0. Okay. So let's take the second part here. When this is 0, right? Because m is a number, it's not 0. T dash should be 0. Okay. So what is T dash? If you pedal back, you can find out what is T dash. Here you are. T dash is lambda r L bar minus R bar plus T. So you can bring it over here and say that T dash equals 0 means this. Lambda r L bar minus R bar plus T equal to 0. Then you can find out an expression for T. So T is equal to R bar minus lambda r L bar. So what is R bar? R bar is the centroid of the actual landmarks. You are given all of the landmarks, right? Reference landmarks, add them together, right? It's a vector. It has x coordinates, y coordinates. Add x coordinates together, divide by the number. Y coordinates together, divide by number. Put x and y. So that is your R bar. What is L bar? This is your estimates, okay, of the references, corresponding pairs, right? Add them together, x, add them together, y, divided by number of landmarks, that is L bar. What is lambda and r? Lambda is the scaling factor, constant. R is the rotation, which is also constant. Okay, but still we do not know what these constants are. But if you find out lambda, if you find out r, then using this equation, number 16, you can calculate t. You are done. So therefore, in this process, you don't have to have this optimization process over 4 parameters, lambda, r, tx, ty. If you can find lambda and r, then t can be calculated this way. So we are reducing the optimization process, is computational burden to a significant level, significantly low level. All right. So now in this equation 15, this minimization process, we have already taken the second part now. It's already done. When you want to minimize the whole thing, you have to minimize the second term as well as the first term. Now let's look at the first term. Now the first term, I want to divide both terms by lambda square root, because I know lambda is a constant, right? In the optimization process, uh, uh, all these terms can be divided by the same number. So nothing wrong with that. So when I do that, this lambda becomes lambda square root, and there's 1 over square root of lambda coming um, in front of the second term. Okay, second term of the first term actually. And then you expand the square so that you get square of the first term and 2 times the product of the two terms, and then square of the second term. All right, like in this equation over here. And now if you look at the first term, it is lambda RLI square, RLI dash square, right? Now what is R? R is a rotation matrix. It's not supposed to change the length of the vector that follows it, right? Just a rotation. The length remains the same, right? So therefore, in the minimization process, R doesn't play any role, okay? So you can take R out of that, right? And try to minimize the rest. That's all right. So when you do that, it becomes lambda times summation of Li dash all things square, and you have a second term, that's fine, keep it there. And the third term, 1 over lambda, right? Because you are getting square, lambda square root becomes lambda, right? Same thing over here. This lambda square root becomes lambda over here. Now the third term is like this, 1 over lambda times a constancy, right? Now, now if you look at equation number 17, right? Forget about the middle term for the moment, right? Look at the first term and the third term. The first term is lambda times some value a, and the last term is 1 over lambda times some value c. So if you have a function like that, lambda a plus 1 over lambda c, right? And you want to minimize that function, right? What you can do is to differentiate with respect to lambda and set it equal to 0 and find out what the lambda is. So when you do that, it comes into this equation, lambda square is equal to c over a. So whatever you have here, second term, that is c, that is summation of ri dash square over summation of li dash square, that is lambda square. So we are now getting an equation for lambda, right? Is that clear to you? C over lambda, C over A. C is this one, sorry, with the summation, and A is this one. Now, if you look at these two terms, you know that these are, you can calculate these things every step of the way, right? All of these reduced coordinate landmarks, modified landmarks, get the square of that. And all of these reference landmarks, I mean, reduce landmarks. This is a constant actually, right? Because landmarks, reference landmarks are not going to change, right? So upfront, you can calculate this quantity. See, so every step of the way, you can do this calculation and find out lambda square, lambda square, and then lambda, optimum lambda is given by this equation 18. It's the square root of summation of Ri dash squares, summation over summation of Li dash squares, right? So without implementing an optimization algorithm here, right? Computationally, you can use these equations to calculate lambda, right? Straightforward. Now you know lambda in equation 18 and equation 16, right? If you substitute lambda here, still you cannot calculate t because you don't know r. So therefore, we need to find out r now, okay? How much you have to rotate the measurements, right? Estimated landmarks, right? In an optimal manner, right? So what is that angle? To find out that, we want to get to the second term over here, right? In the minimization process, this second term is negative. So if you want to minimize the square sum of the error, you have to maximize the second term because it is negative. Okay. So let's maximize the second term. This is the second term. Sigma or summation Ri dash transpose capital R Li Li dash. This transpose comes again, as I explained. Every time you multiply two vectors, you have to figure out one of these vectors, they have to get transpose, right? It should be a row and a column, right? Like that. Otherwise, you cannot multiply. So that's why this transpose comes in. So how can we maximize this for the entire set of pairs, corresponding pairs, right? Let's take one pair, just one pair, right? And try to write down this term, right? What it is. First, you have the reference transform, then the rotation matrix, and then the estimate landmark. So you can write it down like that. You see, the reference first, rotation matrix, some alpha, we don't know what the alpha is, and then the corresponding estimated landmark. And this time, the references and landmarks are actually the reduced coordinate forms of them. Okay, reduced coordinate forms. So every landmark minus the centroid of the landmarks. Every reference minus the centroid of the reference landmarks. Okay, like that. Then you go ahead and multiply this, right? The first, the rotation matrix and the landmarks, right? They multiply. Just one landmark here. And you continue with your expressions here. Try to simplify. Eventually, you get it to this format. So what is that? You want to do this for each and every pair, reference and measured, reference measured, right? And then add them together, right? And you want to maximize it. Now, here you can see eventually the value can be expressed in this format. So what is the first term here? It is the rotation, cos alpha sin alpha. You can think of this as a vector, right? And followed by or multiplied by this one. This is the x coordinate of the reference times x coordinate of the landmark plus y coordinate of the reference times y coordinate of the landmark, right? The first term over here. And the second term right below that minus x coordinate of the reference, y coordinate of the landmark plus y coordinate of the reference times x coordinate of the landmark. So this is entirely the reference and landmark coordinates. Second over here, right? And you know that every step of the way, you know where your reference coordinates are, reference landmarks are, and your estimated landmark. They are x and y coordinates, you know. So therefore, you can calculate this vector. So this is the dot product of two vectors. As I said here, it's a dot product of two vectors. And you want to maximize it. Okay? This is a constant vector. This is a variable vector. This is the only variable part of that expression. You can give various alphas to this one and try to see which alpha gives you the maximum. And of course, the dot product is maximum when the angle between them is 0. Okay, the angle between them is 0. So therefore, the angle here, cos alpha sine alpha, should be the same angle of this vector. So you have to find out the angle of this vector, and that is alpha. Is that clear to you? For every individual pair, you can do that and find out different alphas. That's not what we want here, right? Do it for the entire data set, which means you want to find out this product of all of these pairs. If you have 4 pairs, work it out for all 4 pairs, add them together, divide by 4, and then work out this for all of these pairs and put it as y. When you know x and y, you know the angle. All right. So you want to have alpha looking at the same direction. Then you get the second term maximum. Now see, without going through any rigorous optimization process, we can solve this problem. So finally, because this vector is not a unit vector, right? It can have various values, magnitudes. So what we want to do is to get the angle, the heading, is that you calculate these x and y and divide by the magnitude of the vector, right? Length of the vector. Then you can say this is cos alpha, this is sine alpha. Is everything clear up to now? Equation number 19. Any questions, please? Now, we can calculate alpha here. The moment you calculate alpha, right, you know the rotation matrix, you know R. Earlier, right, in equation 18, we calculated lambda. So when you know R and lambda, you can use equation number 16 to calculate T. All right. So we know these 4 parameters, T, lambda, and R. That will minimize the square error, right, between the reference landmarks and the actual estimated landmarks, right? So none of these estimated landmarks will fall on its corresponding reference landmark, but this minimization process, this alpha, R, and T will make sure that all of these landmarks, the estimated landmarks, will get as close as possible to their corresponding reference landmarks. Okay, that's all what we can do. All right, then the algorithm. So if you want to run an algorithm, this is it. Given the point cloud, so the moment you have the LiDAR map, you know what are the landmarks in the LiDAR map. You identify how many landmarks are there, maybe 30, 40 landmarks, and you know Li, and you know the corresponding Ri. So which reference landmarks are corresponding to these estimated landmarks? You prepare this set of pairs, okay, reference and estimated. So you have m number of landmark pairs actually. Then you start the process. You do the reduced coordinates. So you calculate L bar, which is the centroid of the estimate landmarks, and R bar, the uh, centroid of the reference landmarks. Okay, centroids. Then for each and every landmark, you calculate the modified landmark using this equation. For each reference landmark, you calculate the modified reference landmark. All right. So these modified landmarks, they have two coordinates, x and y. Here also the same, x and y. Now remember, you can use this for not only ground vehicles, for aerial vehicles also. Then you can have x, y, z also, three-dimensional space. So landmarks are now three-dimensional. Let's say you are moving like that, there are obstacles, there are other vehicles moving, other aircrafts moving around you. So they have the XYZ position. In a flock of birds, right, you can see a bird and there are other birds around it. All of these are obstacles, landmarks, not fixed, dynamic. So very complicated situations can be actually modeled like this. So I just want you to not actually customize too much into this problem, two-dimensional. I want you to think about higher dimension also. Okay, right.
So,
And
are
then,
these
yeah, go ahead.
all these are like us, so then given to us in 30, 40 landmarks are all are
Yeah,
given to
yeah, exactly. So the reference landmarks, you need to know where the landmarks are. Otherwise, you cannot localize yourself, no, right? You need to have some reference. What we are trying to do is we have some observations and we want to make sure we want to use the observation and the reference correspondence to shift our position this way, that way, and orientation and scaling and all that, so that we refine our position more accurately, because we know our position estimate is not correct, and that is the reason why we don't see our in our estimates, they are not corresponding to their references, right? The moment you adjust your position, the measured landmarks will fall on top of the reference landmarks. Yeah. So then the third one is the if you want to find out the orientation alpha, you keep accumulating the cosine term and the sine term like that, right? This is equation 19 here, right? For all of these landmark reference pairs, okay? And this is the Ri square, right? Ri square. That is equation number 18 over here, right? To calculate lambda. So every step you do these things and then you calculate your lambda uh, by dividing RR by LL and getting the square root of that. And cosine and sine, this one over here, right? You use it and divide by the square root of their squares, that is the distance, to make it like a unit vector, all right? So alpha is known by this equation, A tan 2 CS, SS over CS, right? This is arctangent or tan inverse in 4-quadrant, all right? So the rotation matrix is now formed using alpha, and T is used from equation number 16. Remember, we discussed, you can calculate T. So the moment you have T, R, and alpha, right? Sorry, lambda, you know the similarity transform, right? You know the similarity transform. So now with the feature-based approach, finally what you do is you have P dash, your new position, RP plus T, right? Um, um, and theta dash, theta plus alpha. You refine your position like that. You refine your position. So now you are not using your wheel encoder base estimate, but after using wheel encoders and calculating your P dash, then you put this similarity transform alpha, lambda, and T to modify it into a new position, right? So like that. So finally, this is our takeaway in a feature-based approach. Uh, though there are so many measurements, right? Now you have 660 beams in your LiDAR, right? Accuracy could fail when there are only a few features. So even though you have a pretty good LiDAR, right, it doesn't help if you don't have features around you, right, to localize. That's the problem. So this is feature-based localization. You need features, right? You need features. Without features, you cannot localize. But there is another way, if you particularly look at indoor localization, right? You can use the walls around you, straight walls, right, as obstacles, and you can localize the robot with respect to the walls. The wall is also sensed by the LiDAR, right? And you can use that information to localize. So we don't regard the wall as an obstacle, right? But it's useful information for localization. So in that case, we call it featureless localization. Featureless localization, right? It doesn't mean it doesn't have any of that, but you have the wall, and with respect to the wall, you can localize. All right. That's it about feature-based localization. Any final questions?
In a LiDAR sensor, one particular obstacles, it has uh, several beams on it. So how do we take the point with this is the coordinate in
Well, yeah. So I think I have shown you earlier the LiDAR map. It looks like this. Uh, LiDAR produces a data file, something like this. Can you see that? This is LiDAR data file, right? So every beam has index, data 1, data 2, like that. So you can think about this as data 1 to data 2 is, say, 1/4 of a degree, 1/4 of a degree, right? It goes like that, and altogether 660, right? So the moment you see, let's say, a 10th beam, you have an obstacle. So it is 10 times quarter of a degree. So that is about 4 degrees, right? From the reference point, 4 degrees, there's an obstacle. 15 degrees, there's another obstacle, like that.
I mean when it's what it's some let's take it is scanning a tree,
Yep.
then the tree contains a lot of beams.
Yeah,
That
yeah,
means
exactly,
lot
exactly.
of points. I think.
That's right. Between two
So
beams, it's
uh,
like a quarter of a degree, So if you think of a tree nearby to you, it covers some, say, 3, 4 degrees. So therefore, it easily gets about 10 or more than 10 beams to detect, to fall on that tree.
so then we take some midpoint around it, take the
Yes,
coordinators.
that's right. So you take the midpoint of the beams as your coordinate. And yeah, so to say the least. But if you want to make it more realistic, you need to get these coordinates, not only coordinates, but like around it. But unfortunately, in case of LiDAR, you don't know the depth and all that, right, of the obstacle. You see only the front face. So the easiest way is to say that, okay, there are so many obstacles in line, but you combine them together, it's one single object. So if an obstacle is long, right, then when you want to localize, you can say the edges, this edge, that edge, and all that, right? In the reference also, you can say this edge, that edge, and get one of the edges and try to localize. Because in the algorithm, we are talking about vectors, right? So vector means just one point. So the moment you get the corresponding point, you are done. With a tree also, right? If it's a big tree, even though there are so many beams falling on it, you can take any beam and localize. All what you need to do is you get the corresponding point in the reference code, because in the reference landmark also there is a range. So you want to get that corresponding point on the reference, right? That point corresponding to the beam. So to say the least, I think it's safe to say that, okay, you get the midpoint of the landmark and the midpoint of the reference and try to uh, coincide the two, right? Is that clear? Any further questions? All right then. So let's wind up the lecture today, and please read these notes. I'll put them on the website and also the video on the playlist so that you can read it again and make sure you understand all these things, right? It's extremely important to know how mobile robots localize themselves. The video you showed you uh, demonstrate the capability. All right. So I think that's it for the day. I'll see you next week.